We have been talking about various kinds of axial flow compressors and their designs in the last few lectures. We have done various aerodynamic issues related to the axial flow compressors, and then of course, we talked about how those aerodynamic theories and understandings can be used to create and design axial flow compressors, blades, rotors and stators. Now, all of it together also has another issue or a serious issue, which we will talk about in today's lecture. This is regarding the noise that is created by the axial flow compressors and the fans used in turbofans, which need to be seriously regulated as per present regulations or traffic regulations all over the world. Now, in the early days of jet engines, when the jet engines started powering aircraft, the main source of noise was the jet noise that came out of the rear of the engine, and that jet noise was the most noise making device or element in the jet engine. Over a period of time, as the engines became more and more powerful, there is another component that became a bigger issue in terms of noise making device. Noise related to compressors and fans in most of the turbofan engines that are used in civil aircraft engines have become such a big problem that the regulatory authorities all over the world have put stringent restrictions on the noise created by various jet engine elements. So, now we have jet engines that noise coming out from the rear of the engine as the jet noise. It also has noise coming out from the front of the engine, which is created by the fans and compressors. And we shall see in today's lecture that one of the reasons these noises have become more and more annoying and need to be regulated is because the aircraft compressors and fans have actually become more powerful, and as we have discussed in the last few lectures, they have actually gone supersonic or transonic. So, when they go supersonic and transonic to create more compressor loading and more compression ratio in a smaller size compressors, they actually end up creating more noise. They are more noisy elements or more noisy machines. Remember, they are aerodynamic machines. So, the noise that comes out of them are essentially aerodynamic noise, and this aerodynamic noise has become such an annoying source of problem that many regulating authorities have put stringent regulation on the noise emanating from these compressors and fans. Many airports in the world have very stringent noise regulations, and if you do not conform to those noise regulations, you cannot operate from those airports. So, the noise regulation has become such a stringent thing, it has now started impacting how the compressors and fans should be designed. And it is one of the reasons, in fact, one of the main reasons why commercial aircraft compressors and fans, fan being the first component in the compressor, have not gone beyond the transonic, or let us say middle transonic Mach numbers, where the tip relative Mach number is of the order of 1.5 or 1.6. The military engines have gone beyond that. So, the technology for making high Mach number fans and compressors do exist, but they are not being used in commercial aircraft engines, and one of the main reasons is noise, because moment you have high inlet relative Mach numbers, the noise coming out of these engines immediately start going up, and we shall see that the noise is very strongly related to the velocity or the Mach number with which the flow is indeed passing through the compressors. So, some of these issues have impacted how the blades should be designed, how the blades need to be finally configured, and we shall see that unless you conform to the noise regulation, your compressor is not going to be accepted commercially and your engine is not going to be certificated for operation worldwide. So, the issues are extremely important, and we thought we should devote at least one lecture on this particular issue, in which we will discuss noise related problems related to axial flow compressors and of course, fans. So, let us take a look at what are the fundamental issues that are involved here, that is creating such a lot of annoyance to so many people all over the world. We shall stick ourselves to discussing noise problems in axial flow compressor. We will not go into the science of acoustics or science of sound making or sound measurement. We will just mention them in the passing, so that you become aware of the science that is involved in this particular problem related to aircraft engines, because the science of acoustics is huge. It is a science by itself, and it involves so many things, and it does involve a lot of high level mathematics. All that is really speaking beyond the scope of this lecture series. So, we will stick to certain fundamental issues, and I will try to bring to you certain fundamental definitions that are used in quantifying the problem that we are facing, that is the noise. And then I will try to mention to you and show to you how this noise is actually measured and how it is actually related to the axial flow compressor operation. And then finally, we will end up by discussing what people are doing to contain this noise. So, noise containment by design to begin with, and then later on by certain containment methodology is a major technological issue with related to axial flow compressors and aircraft engines specifically. The land based gas turbine may not have such a big issue, because most of those compressors are most likely to be subsonic compressors, which do not make such a lot of noise, and certainly not as much as the aircraft engines. So, in land based gas turbine, that noise is not that big a issue as it is in aircraft engines. So, we will stick to certain issues which are prevalent and really annoying issue with relation to aircraft engines. So, first let us get into a little bit, just a little bit, just on the superficially the science of acoustics. We are looking at noise problems in axial flow compressors and fans. Now, compressor or fan noise, as I mentioned, is a different kind of noise than jet engine. So, jet engine creates a heavy noise that is due to the shearing action of the jet coming out from behind the nozzle of the engine, whereas the noise created by the compressors or fan is mainly due to the cutting of the blades, rotating blades through the air at high speed. So, as I mentioned, higher the speed of this cutting, higher is the noise that is created, and this noise escalates as the speed relative to the rotating blade increase. Now, as we have seen, this relative speed or relative velocity, as we used to call it, or relative Mach number, may increase due to either increase of the rotating speed or due to higher incoming axial velocity coming through the intake of the engine. So, either of them could increase the relative velocity or relative air speed relative to the rotating blades. Then, of course, the modern aero engines have gone transonic. Certain of the aero engines which are used in military applications have gone clearly supersonic, and in those cases the noise is far more than that of the old subsonic compressors and fans. So, the problem is manifold today, and as we see, it is directly related to the blade speed cutting through the air, and as we shall see, it is related to the fifth order or sixth order of the blade speed. So, the result is slight increase in blade speed could increase the noise tremendously, hugely, and that is something which the designers, compressors and fan designers and aero engine designers are trying to contain by design and through containment methods. Let us get into certain fundamental issues related to the science of acoustics. Now, fundamentally sound is due to fluctuation of pressure levels and the travel of this fluctuation. So, they travel in waves. Sound always travel in waves like light, and these waves are due to the fluctuations of pressures. If we do not have any pressure fluctuation, we are not going to have any sound. So, a silent zone means that there is no pressure fluctuation going on anywhere in that zone. Sound is typically measured in decibels. This has been derived over a period of years, and it's measured in number of scales, predominantly in A scale, sometimes in B scale. There are many other scales which I will mention, and finally, F scale, which is called the flat scale, and I will try to mention very briefly what these scales are just a little while later. The sound pressure level, as I mentioned, sound is actually a pressure fluctuation. So, sound pressure level is defined as SPL, and that is 20 log 10 P by P reference, and as I mentioned, it is measured in dB or decibels. Now, dB measurement is in number of scales. We will come to those scales just a little while later. Now, in this equation, P is the RMS root mean square pressure fluctuation, and P reference is the reference RMS root mean square of the pressure fluctuation, and this reference is normally 2 into 10 to the power 5 newtons per meter square, which is the normal units for pressure. So, there is a reference that has been sort of universally accepted at the moment, and with respect to that reference, what is the pressure that is operating at a particular instant for creation of sound. Acoustic power is defined as the power watt level or PWL in some literature, in some books, and this is given as 20 into log 10 W by W ref, and that is also in dB, and W is the acoustic power in watts, and W ref is the reference acoustic power in that is normally given as 10 to the power minus 12 watts. So, you see the amount of power that is used by the noise is actually again coming out of the energy that is being transacted within the compressors or turbines. So, a measure of the power does tell us how much of power is literally getting frittered away in creation of noise, rather than being used for purposeful use in aircraft engines. So, acoustic power gives us some idea how the power is going away in the form of noise energy. Now, these are the fundamental definitions of sound pressure level and acoustic power or sound power. Now, fundamentals of acoustics tells us that the pressure changes or fluctuations travel in waves with certain frequency and amplitude. Now, all waves travel with certain frequency and amplitude, and normally higher the frequency, lower is the amplitude, and normally these are associated with the so called high pitched noise, which are indeed also sometimes simply referred to as high frequency noise, and these are normally producing or taking away low power. So, these are the low power noise making frequencies. On the other hand, the high amplitude noise often has lower frequencies, and these are the bass kind of sound, and they often carry high power. So, this kind of sound is often associated with high amplitude. Now, when we are looking at a noise, it is entirely possible, and quite often it is so, that it carries all spectrum of noise frequencies, not just high frequency or low frequency, high amplitude or low amplitude. It carries noise of all many frequencies and many amplitudes. And now, this is often really the case, as a result of which, when you measure noise, it becomes a problem, because you are measuring all kinds of frequencies that are coming out of a particular noise source, not just one particular frequency or amplitude. And hence, you need to actually measure all of them. So, measuring them is actually a very tricky job. So, the noise meters or the sound meters are essentially rather complex machines or complex measuring machines. Many of them are indeed available in the market, but they have been created after a lot of scientific development to capture all these frequencies and then show them up in a certain standard manner, in a certain standardized manner in dBs. And I will come to the scales in a few minutes now. So, capturing the noise in a measuring instrument is another kind of sound, another kind of science. So, we have the science of acoustics, which defines various kinds of noise or various kinds of sounds and tones and so on and so forth, which includes music, which is nice to our ear, but we call something noise which is annoying to us. So, music is very pleasant thing, noise is extremely unpleasant, and we are dealing with noise which are indeed very, very unpleasant, and we have to ensure that those things are eliminated from or reduced as much as possible in operation of civil aircraft engines. So, we are dealing with the science of acoustics. The measurement of sound then becomes a little more complex issue. The overall noise is often measured as overall sound pressure level, or simply called OSPL, which is RMS pressure level of the entire noise signal composed of all kinds of frequencies and amplitudes. So, this is kind of an overall average noise and is often simply measured in terms of dB as the overall noise. So, any machine that you have, the simplest possible noise meter actually gives this value, where all the noise that is picked up by the measuring sensor is converted into an RMS pressure level, and hence it just gives an overall noise in decibels. The more detailed understanding of the overall noise signal is then broken into what is known as spectral components using certain mathematical formats, and this is of course done through Fourier transform, which is typically used in many wave measurements, various kinds of measurement of various waves, and sound being a wave form, it is also captured in Fourier transform. Now, Fourier transform produces spectral density, for which the standard bandwidth is 1 hertz. So, the frequencies of noises are indeed expressed in terms of hertz, and it is normally measured from 0 or 1, or in most measurement machines from something like 10 to 20 kilohertz, that is 20,000 hertz. So, that is the frequency range over which normally the measurements can be made. It is possible that the noise generated could be higher than 20 kilohertz, the frequency of noise, or lower than let us say 10 kilohertz. It is quite possible, but the point essentially is that those kind of noise are normally not of interest to us. Let us see what are the noises that are measured in various scales: A scale, B scale, C scale, D scale and F scale. Now, before we talk about the scales, The human perception of sound is restricted between 10 or more likely 100 hertz to about 12 kilohertz. So, anything less than about 100 hertz, some very perceptive people might hear less than that, and anything above 12 kilohertz, that is 12,000 hertz, is normally not heard by human beings. And so, anything beyond 12 hertz, which are measurable sound in normal measuring instruments, is often called ultrasonic sound. Now, this ultrasonic sound can indeed be heard by some other animals, for example, like dogs or dolphins or even whales. So, there are some other animals who seem to, or owls, who seem to be able to hear ultrasonic sound, but human beings do not hear those kind of sounds. So, as far as human beings are concerned, the sound of interest is normally between something like 10 hertz to about 12 kilohertz. It depends on, it varies from person to person. Some people actually may have even lower perception range than what is shown here. So, but the measurement units normally pick up that range to conform to the human hearing purpose. Now, the human hearing perception capability is captured in the A scale. So, A scale that has been created correspond to human hearing, and lower than that and higher than 12 kilohertz are artificially factored down or toned down in the A scale, and as a result the noise from 400 hertz to about 10 kilohertz are shown dominantly. That means, they are shown on 1:1 basis, whereas the noises below that hertz and above 10 kilohertz are often factored down by in the A scale. So, that is what is called A scale, corresponding to human perception. B, C, D scales are created for various industrial usages, where some of the scales like D are actually factoring in the noise over a period of time, something like maybe 8 hours or 10 hours or 12 hours, conforming to industrial noise regulatory requirements. So, many of these scales conform to those regulatory requirements used in the industries, and F scale typically conforms to flat scale, where all the noise actually that is coming out is picked up on 1:1 basis. So, the entire noise from 10 to 20 kilohertz is picked up in the F scale. So, those are the scales that are typically used in noise measurement. Typically, the noise is nowadays measured in what is known as noise level, which was the acoustic science of acoustics, but it is measured now in what is known as perceived noise level or PNL, and it is measured in terms of perceived noise decibel or PNDB. Over a period of time, people have tried to figure out what is most annoying kind of noise. Certain kind of noise that is most annoying, it actually can vary from person to person. It can vary from one time of the day to another time of the day. Sometimes it carries certain particular tone of noise, which is extremely annoying, and some of these are actually can be captured in the spectrum analysis of the noise meter, and then a correction can be added to account for this extremely annoying tone that is present in the noise, and then this corrected noise is referred to as effective perceived noise and is measured as effective perceived noise decibel. So, EPNDB is what nowadays noise is being measured, especially with related to aircraft engine noise. The pressure fluctuations that we are talking about, which is the source of noise, can be expressed in terms of certain parameters that are indeed used in the noise capturing or noise measurement. where P is equal to cos of alpha divided by 4 pi r into f by a into capital A. Now, capital A here is the amplitude of the oscillating force, in which case there is a pressure fluctuation. F is the frequency of the oscillation. It is being measured at a distance r from the point of observation, or the source of the noise is at a distance r from the point of measurement. So, where you measure is extremely important. Noise indeed does increase as you go towards the source of the noise, and it of course, you measure less and less as you go away from the source of the noise. So, the distance r is extremely important in the noise capturing or measurement business, and a of course, is the speed of sound, and alpha is the angle at which over which the noise is being captured. Typically, you would be measuring at number of angular locations or at an angular distance, and alpha is the measure of that. Now, this allows for an approximate estimate of the pressure fluctuations and may provide an approximate estimate of the power associated with it. Now, as I was trying to mention a little while earlier, the power that goes with the noise is proportional to 6th power of the blade speed. So, a slight increase or decrease of the blade speed would strongly impact the noise and the power that is associated with the noise. So, we have to keep an eye on that blade speed or the relative blade speed very stringently if you want to keep a check on the noise that is emanating from the rotating blades. As I was mentioning, the spectra of the noise can be captured or shown in different ways. One way is the noise meters are designed to measure either in 1/3 octave spectra, which is shown here at the top, which misses some of the details, but it captures 1/3 octave spectra. You can see here the band that is being captured here is from something like 50 hertz to all the way up to 10,000 hertz, which is the normal range of human hearing. But it is captured in 1/3 octave spectra, or it can be captured in full spectra as is shown below here, and entire detail again from low hertz something like 1050 hertz to 10,000 hertz has been captured, and you can see here all the details have been, many of the details which were missing in the 1/3 octave spectra can be captured in the full spectra noise. The instrument that can capture full spectra indeed is as can be well expected, is a costlier instrument, whereas 1/3 octave spectra is a little cheaper instrument, and both the instruments of course can give the overall noise which we mentioned a little while earlier. That is the overall RMS of all these frequencies averaged very quickly and gives in one single value of dB. Whereas, as you can see here at various frequencies the dB levels or SPL levels are different, and as a result at various frequencies the dB levels are different. So, some frequencies the dB is lower, at some frequencies the dB is very high, and those are the annoying noises which need to be somehow cut out, and the designers and the engine designers, the containment people have to work out how to cut out those noises which are coming from particular frequencies. Now, what happens is with relation typically to aircraft blades, engine blades, compressor blades, certain noise peaks are associated with the blade passing frequency. Now, what happens in a blade passing frequency is that one particular blade while rotating passing a particular point in rotation is referred to as the blade passing frequency. It is very easy to calculate that particular blade passing frequency, and that blade passing frequency or blade cutting frequency, a peak is observed here. Now, that is an obvious and most easily identifiable tone that is captured by the noise measuring instrument. And in a old fashioned subsonic compressor, that blade passing frequency was the most identifiable noise source or tone, which is easily at least 10 dB above the rest of the noises as it used to be. In the recent compressors which have gone supersonic and transonic, we can see multiple pure tones. That means, there are many of them mainly due to the shocks that are coming out of the blades, and those shocks create noise, and blade passing frequency tone or that particular frequency noise is kind of mixed up or buried in all the multiple tones coming out of the supersonic compressors or fans. So, the modern engines and the 10 dB gap or safety margin that we had is gone, because there are so many other frequencies at which high noise is indeed happening. Some of them are indeed higher than even the blade passing frequency. So, the noise coming out from axial flow compressors or fans, the modern ones, are indeed of multiple tones, and they are of course more difficult to contain. Now, let us look at what is happening in case when you have a rotor and stator. There is interaction of aerodynamic interaction between the rotor and the stator, and this interaction also creates noise. There is a cutting of the flow that is coming out of the rotor from the trailing edge of the rotor, and then of course, you have blade 1, blade 2, blade 3, blade 4, and then you have the stator 1, stator 2, stator 3, stator 4. Now, what happens is, there is a interaction of this trailing edge which is coming out with the stationary blades. With relation to the stationary blade, remember, the rotor is a moving component. So, the wakes that are coming out are moving wakes, and hence there is a relative velocity associated with the stator and the moving wakes. Now, so those interactions create another kind of noise, and those noises can be two kinds depending on the dynamics of the situation. It can be propagating noise, as is shown on top here. So, it can propagate in waves like this, and it can keep on propagating, or it can be somewhat decaying interaction field, where the noise kind of every particular noise source from B 1, S 1, B 2, S 2 kind of sort of dies off. They do not propagate along as is shown on top here, okay. And each of those interactions die off on their own. So, it could be a propagating interaction field, or it could be a decaying interaction field. So, interaction between the rotor and the stator. So, not only the rotor creates noise, the interaction between the rotor and the stator also create noise, and some of the interactions are indeed in the modern compressors transonic or supersonic. Now, let us see what happens when you have the blades set apart. We know that between the rotor and stator, there is a spacing that is decided by the aerodynamics of the design, and designers actually do a lot of analysis, aerodynamic analysis, before they fix certain rotor stator axial gap or axial spacing. Now, as we can see here, the interaction between the two create a annoying noise, and it has impact on the noise. This spacing between the rotor and the stator has an impact on the noise. As we can see here, the lower the spacing, that means more close they are, higher is the noise. It can be as high as 140 dB, which is extremely annoying and painful to human perception or human ear. If you increase the spacing or the distance between rotor stator to from half chord to 2 chord, the noise comes down, and if it is increased to as much as 4 chords, noise comes down even more. The trouble is, if you increase the distance between the rotor and the stator, it is known that the noise would go down, but it would also reduce the compressor stage efficiency. That means, the rotor and the stator would not then work as one single aerodynamic unit of a compressor, and as a result the efficiency of the compression would actually indeed go down. Now, when the efficiency goes down, it impacts on the overall engine efficiency, overall engine fuel efficiency. But even more importantly, if you separate the rotor and the stator, remember the overall compressor length is now going up. So, rotor stator, if you keep on increasing the distance between the rotor and the stator, the overall length of the compressor is going up, overall length of the engine is going up. Now, this is unacceptable. This is unacceptable to the engine designer, to the compressor designer. Nobody wants a long engine anymore. So, what is good for noise is not likely to be accepted as an engineering solution to the engine designer. So, there has to be a certain amount of compromise between the noise that is happening and the engineering solution of a compact, powerful engine which will power a flying aircraft. So, this is a compromise that has to be done a priori at the time of design before the engine is actually made. So, this is where most of the modern aero engine designers, the compressor designers, the fan designers are spending a lot of time, a lot of analysis in trying to keep the basic source of noise down under operating conditions, various operating conditions of the aircraft engine. If we look at what happens to the noise, we can see that under certain operating conditions, the flow that is going into the engine is indeed different. For example, under static flow conditions, when the aircraft is at the top of, let us say, a takeoff condition, takeoff run, this flow is going into the engine from all sides. So, the noise that is coming out will also be impeded from all sides, or it will be carried with this air on all sides. So, the inflow characteristics during the static test flow or during takeoff is quite different from when the aircraft is flying, when the air is going into the engine in a more uniform manner. So, the manner by which the air is ingested into the engine also would in a way decide how the noise comes out of the engine and is propagated. So, as we can see here, the noise coming out, it is in waves. So, it will propagate in waves like this, whereas in situation like this, it will propagate in waves in all directions. So, in a takeoff condition, the noise very quickly spreads in all directions, whereas in flying condition, it normally spreads straight in the front of the compressor or fan of an aero engine. So, it depends on what the operation is of the engine as to how the noise actually propagates from the source of noise creation. Now, depending on that, the noise that actually can be measured shows that the blade passing frequency, if it is a stationary engine, the noise measured is often higher under takeoff conditions, is normally of a much higher order, whereas in flight condition the noise are of a much lower order. It depends on the fan relative tip Mach number. Typically, during the aircraft takeoff, it uses maximum thrust, and as a result of which the noise created indeed is somewhere over here, which is indeed quite high, could be very high. Whereas, during a cruise at some altitude, the fan relative tip Mach number is normally somewhere down here, and as a result of which the noise, as we can see, is substantially lower than the takeoff or ground static noise. So, noise does depend on the fan relative tip Mach number. We can see here, it also depends on the compressor operating condition. As we can see here, when the compressor is operating under normal open throttle operating condition in flight, the noise is normally somewhat on the lower side. The tip speed of course impacts. On the other hand, if it is operating at peak pressure, that means when the pressure created is high, the noise is higher. This is expected because noise depends on the pressure, that is the source of noise. When the compressor has gone into surge, which is the worst situation from stall, the noise is much higher, and in fact, an experienced compressor operator can make out that the compressor has indeed gone into stall or surge by hearing the noise coming out of it. So, noise actually is easily identifiable when the compressor is surged. It depends on the tip speed. So, as we can see here, the noise values would depend on the operating condition and the operating speed of the compressor or fan. So, these are the issues that are to be considered while indeed designing a particular aircraft compressor or fan, and together they would have to be put together in final design. Now, the noise levels, which as I mentioned are of annoyance to people who are passengers and others who are around the aircraft at the time of operation. The jet noise, which typically creates noise of the order of 90 to about 140 dB. Now, 140 dB is extremely painful. The human hearing is normally good up to about 100, 110. Anything more than that becomes painful. 140 is extremely painful in the sense, if you have to listen to 140 dB for a few minutes, it could impact your hearing capability for a long time. And if you are subject to that kind of noise over a certain period of time, your hearing, human hearing may be impaired for life. So, the noise is a very important issue, and it can be extremely dangerous to human beings subjected to such very high noise. Now, fan or compressor noise of subsonic fans were of the order of 100 dB or thereabouts. Moment it has gone transonic, supersonic, the noises are now of the order of 100 or more. And as we just saw, certain tones, the noises are of the order of 140 dBs. So, noise permitted by regulations is much lower, coming out under certain conditions measured at a certain distance, something like 50 meters away from the engine at a certain angle, under certain operating conditions, have to be between 80 and 95 dB, almost for all kinds of aircraft engines. And these are the noise regulations that have been put in place to safeguard the human beings that are present inside the aircraft or outside the aircraft in the airport, which means that to conform to regulation, the engine designer have to use noise containment or noise suppressing methods, because normally some of the noise is indeed actually much higher than that. So, let us take a quick look at what all things can be done. The noise attenuation, as it is called, or acoustic treatment as it is called in engineering terminology, is normally with the help of perforated metal sheets with certain perforation or porosity level that is prescribed by the designer, and it surrounds the compressor or fan. So, the casing of the compressor or fan is made up of such made with such perforated metal sheet, and around the metal sheet you have honeycomb structures which also absorb a lot of noise. You remember, noise carrying power or energy that has to be absorbed, and that results in a large amount of attenuation or absorption of noise. Depth of the honeycomb structure determines the frequency which is mostly attenuated or absorbed. So, honeycomb structure will have to be designed by specialist to absorb noise of certain kinds, so that most of the high pitched noise is indeed absorbed. Porosity of the metal sheet also has to be determined in a manner which actually attenuates certain kind of noise frequencies. Now, this treatment of using porous metal sheet or perforated metal sheet and honeycomb works best for high frequency noise, which I mentioned earlier actually carries low power. The high amplitude noise which carry high power are actually more difficult to attenuate, and now we know why, because they actually carry high power. So, most of the noise that is annoying to our ear are essentially high frequency noise, and they need to be indeed attenuated or absorbed by certain mechanical means, so that at least the minimum safety is guaranteed for the people who are around the aircraft. So, we have seen that a number of issues are involved here. There is a lot of aerodynamics, there is a lot of mathematics which we have not done, the science of acoustics, all that needs to be factored into the understanding of the noise, and then the fan or compressor designer would have to design compressors that conform to this noise, and only then it goes on to the aircraft. So, the modern compressor designers would have to conform to noise regulations very stringently, otherwise his compressor or fan is not likely to be accepted by the commercial engine designers. So, this brings us to the end of a discussion on various aspects of axial flow compressors and fans. We have discussed various things, but more predominantly we have discussed the aerodynamic issues that are related to the axial flow compressors and fan. Now, we will move on to the turbines, and to begin with axial flow turbines. So, in the next class we will introduce the axial flow turbines, the fundamentals of axial flow turbines, and we shall see that it is a different kind of machine, and that is what we will do in the next class, axial flow turbines, an introduction to axial flow turbines.